In a prior lecture, we began discussing in detail how to calculate the rotational kinetic energy for a rigid system that is rotating about an axis passing through the system's center of mass. In this lecture, we're going to complete that discussion by working two examples that involve rotational kinetic energy. First, let's consider this case. A thin rod of uniform density whose mass is 1.2 kilograms and whose length is 0.7 meters rotates about an axis passing through the rod's center of mass perpendicular to the rod. The angular speed of rotation is 50 radians per second. What is the rotational kinetic energy of the rod? Here's how to solve this problem. We're asked to find the rotational kinetic energy, which we know is equal to 1/2 times the moment of inertia times the square of the angular speed. We're given the angular speed, but we don't have the moment of inertia directly. We can calculate this if we know the expression for a thin rod's moment of inertia about an axis perpendicular to the rod passing through the center of mass. We can find this expression in the textbook or by looking back at our earlier lecture on rotational kinetic energy. The moment of inertia for a thin rod is 1/12 times the total mass times the square of the rod's length. We insert this expression into our formula for the rotational kinetic energy, then insert the numerical values, and we find the kinetic energy here. Notice that in our accounting for units, measures of angles, here in radians, are effectively dimensionless and, as a result, don't appear in our final result. Let's now discuss this example, which requires employing our fundamental principle, the energy principle, in a case involving rotational kinetic energy. A uniform 6 kilogram disc of radius 0.3 meters is mounted on a horizontal frictionless axle. Initially, the disc is at rest. A string of negligible mass is wrapped tightly around the rim of the disc. The string is pulled tangentially with a constant force of 15 newtons through a distance of 1.8 meters. What is the final angular speed of the disc? We start with a fundamental principle, the energy principle. We know this is a good choice of principle to start with because we are asked to find an angular speed which shows up in the definition of rotational kinetic energy. To apply the energy principle, we choose the system of the rotating disc plus the string. The string is important in that it provides one way for the system to interact with a contact force in the surroundings, but otherwise the string plays no role in rotational motion because the string is massless. We sketch both the initial and final states of the system. At this point, we can identify what energies are changing in the system. The disk is not translating. There are no changes in thermal energy, potential energy, or any other energy, so the only energy change we have here is the non-zero change in rotational kinetic energy, which means there must be energy transfer between the surroundings and the system. The wheel is mounted horizontally, which means the Earth acts on the system by means of a weight force acting downward at the disk's center of mass. There is a contact force of some unseen agent pulling on the string to the right, and the axle interacts with the system with a separate contact force, which must be pointing as shown by this arrow. Here we're applying Newton's second law. We observe the translational motion of the system is unchanged, which means the change in momentum over the change in time for the system is zero. Therefore, the total net force on the system, the sum of the three forces shown here, must also be zero. So that means the arrow representing the axial contact force must look something like this. However, for the energy principle, what we're concerned with here is energy transfers by work, which can still be non-zero even if the net force acting on the system is zero, because we have to look both at the forces and the displacement through which each force acts at its point of application. The weight force acts at the center of the disk effectively, which does not displace, so the work done by the weight force is zero. For the same reason, the contact axial force, also acting at the center of the disk, does no work. However, the pulling force acting on the string acts through a displacement that, in magnitude, is equal to the 1.8 meter length of the string that unwraps from the disk. So this pulling force, which acts parallel to the string, does non-zero work that is equal to the magnitude of the force times the magnitude of the displacement, which we symbolize with the letter D. Now, the change in rotational kinetic energy is the final rotational kinetic energy minus the initial rotational kinetic energy, where the rotational kinetic energy is 1/2 times the moment of inertia of the disk times the angular speed squared. Now, since the initial angular speed is 0, the initial rotational kinetic energy is 0. So, by inserting all this information into the energy principle, we end up with an expression that has the final angular speed in it. Now, at this point, we need an expression for the moment of inertia of the disk about an axis perpendicular to the disk and passing through the center of mass. We can look this up in the textbook or look back at our earlier lecture on rotational kinetic energy. We find that the moment of inertia of the disk is equal to 1/2 times the mass of the disk times the radius of the disk squared. We put this in and do a little algebra to solve for an expression for the final angular speed. Once we plug the numbers in, we can obtain the final result. We will work with more examples involving rotational kinetic energy in future lectures. However, as a final note for this lecture, we point out that we've emphasized here rigid rotation about an axis passing through the center of mass. It's of course possible to have rigid rotation about axes with fixed orientation that don't pass through the center of mass. We can show such cases can be described using the framework we introduced earlier when we distinguished the energy of the average motion, the translational kinetic energy, from the internal energy using a result known as the parallel axis theorem. Specifically, we can show that the kinetic energy of rotation with an angular speed omega about an axis not at the center of mass is equal to the sum of a translational kinetic energy, 1/2 times the total mass times the center of mass speed squared, plus the internal kinetic energy of rotation at the same speed omega about an axis passing through the center of mass with the same orientation as, or in other words, parallel to, the original axis. In the energy problems coming up, we'll prefer to maintain the separation between the translational kinetic energy and internal energies like the kinetic energy of rotation about the center of mass, because we'll then be able to use some powerful procedures for solving such problems with the energy principle. We'll start discussing these procedures in our next lecture.